So let's start. What will I say today? I will speak mainly about finite element method. Why? Because our software is based on this. I will speak about other numerical techniques to solve vibroacoustic problems and in general. As I said, we are using mainly finite elements, so maybe I'm a little bit partial on finite elements. Be aware of that. But I will try to be as objective as possible. I will speak about some other alternative techniques related to finite elements, especially when dealing with exterior acoustics. Obviously, finite elements, they are a way to divide parts or geometry into small elements. When you are dealing with exterior acoustics and have an infinite medium, you can be in trouble easily. So there are ways to solve this issue. I will speak about some applications and especially transmissions of sound crossing complex panels containing porous materials. Also some applications about vibroacoustic behavior of a trimmed vehicle or trimmed panel within a vehicle, more exactly. And then, if I have time, I will speak about modeling arrays of ducts, which can be seen as a special class of porous materials. And in some case, I will show you, if I have time, that we have to go further than equivalent fluids modeling using a double equivalent fluids modeling. So first of all, analytical versus numerical approach. It's not really different in my opinion. Both attempt to predict the behavior of physical systems to help solving engineering problems. And they start from a mathematical description of some physical phenomenon. Usually it's described by a set of coupled partial derivative equations. And those equations are the same in numerical approach and analytical approach. It's the way to solve those equations that usually will differ. One example of such an equation that is very well known is the sound propagation equation. In this case, I've written it in a non-homogeneous medium. If you assume that you have constant bulk modulus, constant density, you end up with a well-known Helmholtz equation. Usually those partial derivative equations are difficult to solve exactly, especially when they are used in a geometrically complex system. So we usually need some simplifications or approximation to get a solution. And maybe we can distinguish analytical versus numerical approach there. Analytical approach used to be a way to solve those equations by hand. Well, nobody is doing it by hand anyway, but let's say we try to solve the equation by simplifying the equation itself or the geometry on which it's applied and getting an exact solution. While numerical approach, they do not simplify the geometry or the equation, they try to find an approximate solution using a discretization technique. What is a discretization technique? It's very general. You have an infinite set of functions that could solve the partial derivative equation, and you cannot find your solution in this infinite set of functions, of fields. So the idea is to find an approximation in a finite subspace of this infinite space of possible solutions. And there are a lot of discretization methods, and maybe we can distinguish numerical approach by those discretization methods. You have maybe the earliest one, the finite difference, very well known, not much used in vibroacoustics. Then you have finite elements, almost as old, which I will speak a lot about, and I think they are the current main generic technique used in commercial software for low frequency approaches. You have finite volumes, discontinuous Galerkin approaches, which are somewhat similar to finite elements and much more used in fluid dynamics. Boundary elements, they were used a lot for exterior acoustic problems because they do not suffer from the difficulty of discretizing an infinite medium. But they are a little bit less used now for some reasons I will explain later. And you have wave-based method where you can start to enrich finite element methods with some wave solutions, and then you go to solutions that do not solve directly the same equations as the PD itself, but do some ray tracing, like some high frequency approximation, a little bit like optics. And then you have other methods that are a little bit different, also lattice-Boltzmann, which do not directly discretize the PDE, but can be shown to be equivalent under certain circumstances. I will not speak more about that. It's also more used in CFD. And you have the SCA approach that, well, it's really between numerical approach and analytical approach. I will speak a little bit more about that later. So why simulation techniques, being analytical approach or numerical approach? Why do we try to simulate reality instead of directly measuring it? Well, many reasons for that, but maybe one of the main reason is that the design cycles tends to be shorter and shorter, and we cannot afford to make design errors, especially late in the design process, because it's very expensive. So you would like to test a lot of possible designs. It means a lot of different prototypes, testing a lot of things, and looking at what happened. It's both expensive and too time-consuming for the short design cycle. So the idea is to complete the classic prototype approach by virtual prototyping, trying to simulate what will happen without having to build actually the designed device. Maybe a short comparison, simulation versus experiments, what you can gain from both and why they are complementary. If you want to understand what is happening, it's better to turn to experimental methods, because if you don't know what is happening, you cannot even have a mathematical description, a correct mathematical description of the phenomenon. So neither analytical nor numerical methods will work. Why is it happening? Then analytical methods are extremely interesting. You can get a lot of insight. And numerical methods are very helpful also. They give very detailed information that is very difficult to get from experiments. How you can change it? Well, there it's really the numerical methods that are king. Why? Because you can do a lot of change, including the geometry, even making it very complex, and this is usually more difficult with analytical methods. With experimental methods, well, you have to do a lot of tests, it's very costly. And the cost, as I say, is very high for experimental methods, very low usually for analytical methods, because they are not CPU intensive, or they try to be as cheap as possible. And the numerical methods, they are medium. They can need very powerful computers. Still, it's cheaper than doing prototyping. Different approaches, as I said. Finite difference, the oldest one. Variational formulation, like finite element method in finite elements, I will speak about it. Integral formulation, boundary element method, I will also speak about it. And then, starting from BEM already, we have to make some assumption, because we cannot consider, for example, using boundary element method, non-homogeneous materials. When you do ray tracing, you are doing some hypothesis about very high frequency, and you are not solving the PDA directly, you are solving a ray approach for wave. And when you do SCA, you are doing a lot of time averaging and space averaging, and basically are building some kind of analytical or experimental energy model of your system. One big question you have to answer quickly when you go to a numerical method is, do you want to simulate your system in the time domain or the frequency domain? Well, most of the porous materials will use a frequency domain approach. Why? Because you have some things that are easier in frequency, everything linked to memory effects, damping, internal variables like in viscoelastic materials are much more easy to deal with in the frequency domain. Basically, it's just frequency-dependent complex properties. In the time domain, it's much more complex. Usually, you have to retain some kind of history for each of your material particles to be able to solve that. And it can be costly, it can induce issues in stability and so on. So it really depends how complex your materials are. But if they have a memory and complex damping, usually it's much more easy to go to the frequency domain. For which frequency range? You have some approaches that are more well suited to low frequency and some more suited to high frequency. Finite difference, finite element, BEM method, all of them are very accurate, directly solve the PDA equation, but they tend to be very costly when you increase frequency for reasons I will show later. Then you have high frequency approximation like SCA or ray tracing that do not work at low frequency. And then you have the mid frequency, which is the more tricky frequency regime, where you have some kind of mixed approach, where you can put some energy-based finite element approach, or what we have developed in our company, virtual SCA. You can see those methods like a bridge between the low frequency world and the high frequency world. So when I say low and high frequency, what do I mean? The behavior of the systems are quite different in low and high frequency. In low frequency, you have, usually when you have a structure, you have individual modes that are clearly responding independently. They are well separated. They can be observed when you're doing a frequency sweep. At high frequency, the modal behavior is lost. Basically, all the modes are non-identifiable. The damping is larger, so you don't really have a modal behavior anymore. And mid-frequency, well, it's again a mix between the two. You still can see some modes, but not all of them, and damping makes identifying a specific mode already difficult. But you cannot forget about a modal behavior. Some of them will still appear. When you have unbounded medium, you don't have modes as such. So there the high frequency versus low frequency is a little bit defined a little bit differently. High frequency is when you have short wavelength compared to the geometry you are studying, and you can use approximation like rays. And low frequency, it's the opposite. It's when the wavelength is larger or comparable to the size you are studying, and you cannot really use a ray approach. So very quickly, the oldest numerical approach, when you have a PDE you want to solve, maybe the more natural way to tackle the issue, is to discretize your unknown solution on a regular grid and just use a stencil expression that gives you the special derivative of first, second order, like a gradient Laplacian, in function of the values of the unknown field at the grid points. It's very easy to understand, and it directly uses the coupled set of partial derivative equation. It's able to handle very large models because it's very well optimized. It can run in parallel on GPU, but it has some drawbacks. The original method is developed on a regular grid. You can use deformed grids, but it's start to be a little bit more complex already. And then it's not enough to deal with really complex problems in terms of geometry, so you need to go to non-congruent grids where you have multiple grids that overlaps, and it adds a lot of complexity. When you have multi-physics, it's even more difficult because you have the boundaries between the physics to track, and it makes things difficult. So this method is not so attractive for modeling complex systems made of many geometrically complex parts. That's probably the reason why it's not so used in vibroacoustic problems. Finite element analysis, very shortly, it's very well known by engineers. It's working by dividing your geometries into small congruent elements. It's also able to deal with very large models. It easily couples multiphysics, and basically for structures, especially thin structures, is really the method that is used everywhere. It's the standard method. It's very difficult to beat in terms of performance and flexibility. It can deal quite easily with multiphysics with a single method because it's able to discretize very different sets of PDE. Model approaches are possible. And for acoustic fluids, you have to use a 3D mesh. It's used to be an issue, but the measures, finite element measures, have made a lot of progress, so it's no longer really an issue. That's why I guess it's something that is extensively used now for commercial vibroacoustic codes. You have a lot of variants for finite elements method. The classic finite elements, I would say it's the interpolation shape functions are mid-order, linear, quadratic, sometimes higher order, and they are continuous. You have finite volumes, more often used in CFD, which is lower order and discontinuous. You have DG, which is like a mix of the two, high order but still discontinuous. And you have a lot of variations. Some of those variations offer especially efficient solution scheme, but they are usually in the time domain. And for, as I said, for thin structure, shells, beams, really linear or sometimes quadratic finite elements, classical Galeckian finite elements dominates the field. Boundary elements. Early works for exterior acoustics were usually based on boundary elements. Why? Because they naturally deal with sound radiation. You only have to mesh the radiating surface, and the number of degrees of freedom because of that is much lower. But you end up with a dense system of linear equations, while finite elements you create a sparse systems of linear equations. So which method is the more efficient is not so easy to tell. Usually for, at least for lower frequency, finite elements is faster. For when you increase frequency, boundary elements become faster again. It's difficult. But the main drawback of boundary elements is that you need to have a homogeneous acoustic domain, meaning no mean flow, no temperature gradient, no different fluids, no difference in properties. So it's a big limitation, and also it's more difficult to couple with finite element used in the structure. So basically, finite elements is not necessarily faster. Sometimes it is, sometimes it is not, but it's definitely much more flexible than boundary elements. Okay, you have some other issues like spurious frequencies and so on, but I will not go into details. Typical boundary elements analysis. You can see it here. You have only to mesh the boundary of the vibrating body, but you also have to create post-processing mesh, because as you don't have any degrees of freedom outside, if you want to visualize the pressure field, you have to do a special post-processing steps there. Common challenge between finite element analysis, boundary element analysis, and usually all discretization-based techniques is that the cost of those analyses grows very quickly with frequency. Why? Because you have to discretize oscillating fields, so you have constraints based on the wavelength, on the element size or grid size if you use finite difference. So as you see, the CPU cost increase like the 7th power of frequency for finite element analysis, like the 6th power of frequency for boundary element analysis. So you have, well, the scaling factor is different. Usually finite element is better at lower frequency, but you have a crossing point. You also have a big issue, especially in finite elements, is dispersion, meaning that your amplitude is well predicted, but the phase is different because the numerical speed of sound is different from the actual speed of sound, and it can lead to errors in eigenfrequencies predictions or some issues when you have different techniques where you have to match the waves. So usually for big problems, it's the main source of errors, and it's the biggest constraint on the element size. Another issue also linked to frequency a little bit is the variability. Usually, especially when you increase in frequency, it's very difficult to get repeatable experimental results. Not only because you have some experimental errors, but also because what you are measuring, what should be the same device repeated, is basically not exactly the same. A small tolerance error or difference in material properties tends to change a lot the response at a particular frequency when you go to high frequency. So you have a lot of variability, and this is an issue already mentioned yesterday by Noureddin, meaning that if you go to very accurate numerical procedure to predict your model and end up predicting a single curve while in fact you have a lot of dispersion in your experimental measures, well, maybe you overdo the simulation. Another technique used for high frequency, or well, maybe more in room acoustics, is the ray tracing technique. It's very similar to ray tracing in optics for rendering computer scenes, for example. But instead of light rays, it uses sound rays with the same concept of absorption, specular and diffuse reflections. You don't have really interference, no phase anymore. So that's why it's not a low frequency approach, and there is no diffraction either, or sometimes you have simplified diffraction correction. I will not go into details because we don't have this method. It's really focused for high frequency and room acoustics. Statistical energy analysis. It's a high frequency analysis method based on production of a reduced model based on energy exchange between subparts of your model. You have to decompose your structure into subsystems that are weakly coupled, and then you have some analytical prediction of the way energy is stored, dissipated, and exchanged between those subsystems. Problem is that it's not easy to define substructuring that is weakly coupled and for which each subsystem can be reasonably well described by some analytical model based on infinite curved on flat plates or beams or stuff like that. So it's not so easy because of those two issues. Alternative we have developed is based on the same concept of reduced energy model, but it doesn't really assume weak coupling or coupling only at contacts between subsystems. Neither use analytical description for predicting damping and vibration energy storage. So basically, how do we proceed? We emulate with finite elements something that is done experimentally when you are doing experimental SEA. You just inject energy a little bit everywhere in your subsystems. You measure vibration energy in each subsystems, and you basically build a database of how injecting energy somewhere affects the energy in other place. And you assume linearity, you invert the system, and you build your energy model like that. This works for much lower frequency than classical SEA, and it's quite robust in terms of definition, but obviously you need a finite element mesh, and usually a model representation on this mesh. Good news is that it's often available, at least for cars. Okay, this I will skip, can go in more details if you are interested later on, but it shows a little bit how the method is implemented. Here, comparison showing it works well, obviously, because this is our marketing material, but indeed it works well for a large ways to divide your subsystem. It's not really sensitive like classical SEA, but it's much less predictive. Also, you already need to have a correct finite element model. Okay, speaking about finite elements, I will go in more details because that's what we use, and I already mentioned that it's kind of standard for general vibroacoustic commercial code now. Maybe a good way to address this problem is to start from scratch for a simple problem, the acoustic wave equation. So if you assume that you have small pressure fluctuation propagating in a fluid of non-compressibility and density, but those can vary in space, you can start from continuum mechanics and derive a partial differential equation model for the fluids and pressure fluctuation in this fluid. Well, it's classic. I will not go into too much detail. You start with a momentum conservation, fluid compression, you combine the two, and you end up with this equation. There are various ways to do it, but you have to be careful if you are interested in this, because you can end up with incorrect results when you have non-homogeneous properties for compressibility and density. But this is the classical one that is correct for varying properties like density and bulk modulus. Should we go to frequency domain? Well, not necessarily. We could solve this in the time domain, but if we have history-dependent physical properties, like, for example, here, a compressibility that includes some losses, some hysteresis, then we probably gain from going to the frequency domain. Another example is all the equivalent fluid models you have seen yesterday. They all have very frequency-dependent properties because they basically use a simplified model to represent something that is very complex, where you have a lot of histories hidden between the fluids and the skeleton that has been eliminated. So basically, as soon as you have damping or complex frequency dependence, you go to frequency domain. So you end up with this equation. It's the same as this one, but which has been Fourier transformed for the time variable. And you have this equation for the pressure. If you are interested in the acoustic velocity afterwards, you can get it from a gradient operation. Something that you can see already is that each frequency is independent from each other, meaning that you can, if you have multi-frec problem, you can solve it in parallel from quite trivially. So that's a speed up very easy to have for frequency approach. A drawback is that all the properties and the unknown fields are now complex while they were real in the time domain approach. So now we have a PDA, complex PDA to solve. How we do it? Either a straightforward approach, finite difference, I don't have to do anything more on my PDE. Or you can use a variational approach. Basically, you have to build the weak form, which is just the PDE multiplied by a test function that is completely arbitrary. And you can show under certain hypothesis that if this is true for all test functions, well, this has to be fulfilled everywhere in the domain. Then you use the green theorem cleverly to reduce the requirements on the continuity of the pressure fields that will help during the discretization process. And it will also show what we call natural boundary condition. It will show more naturally what kind of boundary condition we can impose. This is not a very formal derivation, it's a quick derivation, so please excuse if I make some mathematically unsound things here. But basically, once you have done the green theorem, you end up with a weak form integrated in the volume plus a surface expression, which is called the natural BC. It helps introducing boundary conditions that are essential on the field itself, weak on the normal gradient of the fields, and mixed, relating the fields and its normal gradient. In acoustics, it's very useful. For example, Dirichlet is imposing the pressure. It's not so often that this happens, but the Neumann is imposing the normal velocity. This happens all the time when you have a vibrating body leading to sound radiation. And the Neumann, the Robin mixed condition is something that can be used for implementing admittance boundary condition. Okay, so why the natural BC? When you don't impose anything on some part of the boundary, you end up with this that has been fulfilled because it has to be verified for any test function here. So this is the natural boundary condition that happens if you don't do anything. That's why it's called like that. Okay, the Dirichlet boundary condition is imposed pressure. Neumann, as I said, is imposed normal velocity. Robin is admittance. So you have a region where you impose the normal velocity, a region where you can define an admittance boundary condition relating pressure to normal velocity, and all the other walls have a zero normal velocity, so they are impervious walls. Natural boundary condition for this discretization, for this weak form of the Helmholtz equation. Okay, still I don't have a numerical approach because I have to discretize now my fields to have a finite set of possibilities instead of finding the solution in an infinite set of functions. So the idea is to use, for finite elements at least, to use piecewise polynomial functions for approximating the pressure field or any field you want to approximate. It have enough continuity for the weak form, but it's also zero almost everywhere except in a very narrow range around its one value. So most of the residuals will vanish. And solution is obtained, because of that, solution is obtained by inverting a very sparse linear system. And it remains doable for a very large number of degrees of freedom. You have the Galerkin finite elements version. It uses test functions that are the same as the shape functions. It's the classical one that is used everywhere in structure. It's used also for acoustic fluids and, as you will see, for porous materials also. It's very interesting. It's have optimal convergence for elliptic problems. It also have some energy or virtual work interpretation. So the solution will minimize the free energy if you use Galerkin approach. And this will, as we will see, help energetic post-processing of results. So it's very nice for solving structural or elliptic problems. This is a wave equation solved in 1D. This is the type of sparse system you end up with. It's similar to finite difference in this case, but for 2D or 3D it's more complex, but still very sparse. Okay, I speak about the mesh. Obviously, you will have as many degrees of freedom as node in your mesh. So you would like to use big elements, but you cannot. Why? Because you have to discretize an oscillating field. So a basic rule of thumb is at least 6 linear elements per wavelength. Usually it's not enough. Why? Because you have other constraints. You have small openings or geometrical details that can lend to smaller elements. You can have singularities or have to describe non-homogeneous properties in your material, for which you will need to use the mesh also. And so you can need to have smaller elements, at least in some parts of the mesh. You can have adaptive meshing. The mesh have progressed a lot, so it's very possible to change the mesh with the frequency and gain some CPU time like this. Your other complexities is, and this Noureddin has spoken about that yesterday, is which wavelength to use. For acoustics, it's quite simple, at least for isotropic acoustic propagation. As soon as you have structure, it's much more difficult. You have bending wavelength, you have shear wavelength in some cases. In porous material, it's even more complex like that. You have 3 wavelengths at least, and more than that, they are damped. So wavelength itself is not easy to measure. It's not directly linked to sound speed and frequency. So yes, 6 elements per wavelength, 6 linear element per wavelength, but it's just a rough rules of thumb. Why the F7 dependency in frequency? Well, now that we know that the number of elements is directly linked to the wavelength, which is inversely proportional to the frequency. In 3D, you will have f to the 3rd power number of elements if you respect this rule of thumb. So f to the cube number of degrees of freedom, but the bandwidth of your sparse matrix will be f to the square. If you combine the two, you know that the CPU time for inverting such a matrix is number of degrees of freedom times bandwidth to the 2nd power. It's the 7th power of the frequency. So increase very rapidly. It means that even if the CPU power increase rapidly with Moore's law, frequency will remain an issue for the foreseeable future for finite element approach. Classic reduction technique, as I say, you can do modal analysis. I will not go into the details of modal analysis, but what you need to know is that there are solutions of the problems without excitations. So homogeneous solution, if you want, for certain eigen frequencies. Those eigen modes and associated eigenfields are heavily used in commercial code as a reduction technique. Instead of using directly the degrees of freedom at the nodes, we start by doing an eigenmode extraction and then use participation factors for each eigenmode as degrees of freedom. That's what we do for real eigenvalue problems. So basically undamped problems that have a mass and stiffness matrix. But for complex value problem, it's not so much used because the CPU cost of modal extraction is too large. It's much less robust, so it doesn't, it's not as straightforward for doing modal extraction. So it's more used for stability analysis, some investigation, but not really as a reduction technique. The problem is that what we are dealing with now, porous materials, acoustic radiation, all of this, viscoelastic solids and so on, all of this involves damping. So it means that we will not be able to use real eigenvalue modal extraction. But still, usually we have some parts of the model like the thin metallic structures that are have very low damping. And for those, we usually will use modal extraction to reduce the number of degrees of freedom. Just a simple example for acoustic cavity, the eigenmodes, they are well known. Maybe something to mention is that when you increase frequency, the modes becomes much more shaky and sometimes local, and you cannot really identify them from an experimental modal extraction. You have too much variability, and so those modes are still useful for numerical speed-off of your simulation, but as helping the understanding of the system behavior, they are not so useful anymore. Okay, exterior acoustics. As I said, I mainly focused on finite elements, explaining how to model a finite model dividing into a set of finite elements. But when you have exterior acoustics, you cannot do that, because as elements have a fixed size with respect to wavelength, you will end up with an infinite number of elements if you want to pave an infinite medium, and this will not work. So you need to have an alternative approach than just using finite elements as the single method. The first method that was used for dealing with that was boundary element methods. It's based on an integral equation which relates the pressure at any point to the pressure and normal acoustic velocity on a closed surface. Well, that's the simplest version of boundary element method. As you see, you have pressure here and here. So if you say, I want to evaluate the pressure at some points of my closed surface, you can imagine that you end up with an equation to solve. So how it is done? You have to discretize, again, like for finite element, your pressure field, but this time it's discretized only on a vibrating surface or a closed surface. On the nodes of the mesh, you will have a classic finite element shape functions representation for the pressure field. And for each node of the mesh, you can express the integral equation I have written before, but you split it by doing the integration element by element. You end up with something like that, and you assume that you know the normal velocity everywhere on the closed surface. You have to solve the pressure here, because you end up with 2 times the pressure. You end up with a system of equation. 2 difficulties compared to the system of equation you obtain with finite elements. Here you see that you will couple nodal pressure with all the other nodal pressure. So you don't have a sparse matrix anymore. You have a dense matrix. The other difficulty is that the matrix itself is not so easy to build. You have numerical integration that are more tricky to perform than finite elements, which use nice polynomial shape functions. Here you have green functions that have singularity, because they depend on 1 over the distance between the 2 points. And these integrations are not so easy, at least when you are doing it on the surface, especially for self-influence. So you need to use some tricks, like going to polar coordinates or using singular integrals. Well, I'm not going to details. I'm not a specialist of boundary elements, but you have to know that building the system before inverting can take some time, and that's the reason why you have this crossover in terms of performance, where finite elements are more efficient at lower frequency, while at higher frequency the gain in frequency scaling from boundary elements become interesting. Main issue is that you need to have the green functions, and those are analytically available only for simple medium, usually infinite medium of homogeneous properties. And that's the main drawback of the boundary element method. Okay, another drawback is that you have the pressure only on the boundary, but you can bypass this drawback by using post-processing. Once you know the pressure which has been solved and the velocity which is known on the vibrating surface, you can very easily, using the same integral method, compute the pressure at any point outside of the vibrating skin of the structure. Okay, so this is the typical results where you have the pressure computed on the skin, which was solved by inverting this full system, and then you have the pressure that is post-processed on any external points or mesh using the integral equation. A very simple form of boundary elements was mentioned by Noureddin yesterday. It's the Rayleigh surface. Basically, if you have a flat surface, the integral equation simplifies because the green function normal gradient vanish on this plane for excitation that is located on this plane. And so you have only the normal vibration that appear, and the pressure does not appear in the integral form. So you have an explicit form for the pressure, and it can give you directly, once you know the vibration on a flat surface, on a buffered flat surface, you can get the pressure anywhere in the half space. And if you need to couple that with a vibrating plate, you end up computing the pressure on the plate itself, and you end up with a impedance-like contribution for the plate. Be careful, it doesn't add any degrees of freedom to the vibrating plate, but it will couple due to this integral, it will couple every nodes on your plate with every other, while if you don't have this condition, a node is coupled only with its neighbor using finite element shapes. So it doesn't increase the number of degrees of freedom, but it fills out the matrix, so it still costs some CPU time. Okay, now if you are using FEM, how we can deal with free field radiation or far field problems. As I said, boundary elements were the first method used to do that, but they have limitation for non-homogeneous fluids, like if you want to consider thermal gradients or non-homogeneous mean flow. And they have some robustness issues also, some irregular frequencies that are difficult to solve or costly to solve. So there was a need to add some ways for the finite elements to be able to solve unbounded problems. The first approach is a very, very simple one. When you are dealing with the exterior acoustics, you have a condition that is called the Sommerfeld radiation condition that defines the asymptotic behavior of the pressure field far away from all the radiating or acoustic sources. It's linked to the far field energy flow that has to be outgoing, that cannot be ingoing. You know that this relation should be satisfied approximatively if you are far away enough, even if you are not at the infinity. And if you look at this expression and get back to the expression of the velocity in terms of pressure gradient, you will see that basically this expression is equivalent to imposing an admittance far away from the radiating body on a sphere, an admittance that is equal to the specific admittance of the fluid medium, rho c. And this is very simple because it's, as you saw, imposing an admittance boundary condition for finite elements is quite trivial. So it works well. The issue is that you have to create a sphere that have a radius quite large for that to be accurate. And so it means you have to include a lot of finite elements in your model. And so It's simple, it works well, but it's costly. So people try to do better. One way to do better is to say, okay, why do I have to put such a large amount of finite elements before putting my admittance boundary condition? It's because I have to let non-normal waves reorganize until they reach the far field condition where all waves are normal. They are radial to compared to the acoustic source that can be considered as a point source at this scale. So the idea would be maybe we could reduce the size of the amount of finite elements, the size of the finite element domain, by damping more progressively the waves, not damping them with a single boundary condition. And that's the general idea behind the perfectly matched layer. The idea is to progressively absorb the waves so that it doesn't perturb them so much, even if they are not normal. And the PML method optimizes the properties you will put in this progressive damping so that it's optimal. The way to do that is to damp only the outgoing waves, but not the waves that are not propagating in the radial direction, that are propagating in the tangential direction. The mathematical approach to do that is to stretch the radial coordinates using a complex factor. It's nice to do the analysis. I don't like it because the physical interpretation is not so easy. But there is another way to describe PML that I prefer because it's much more physical for an interpretation, is to update the bulk modulus and use an anisotropic density for the fluid. Anisotropic density seems strange, but you remember for equivalent fluids, density is linked also to viscous effects, and having viscous effects different in one direction or another is not strange at all. So anisotropic density is possible if you want to damp something. And we would like to increase damping progressively, but not change the radial impedance, because abrupt change in impedance is what is causing wave reflection. And we don't want to change the tangential speed of sound either, because this would change the way tangential wave propagates. So how to do that? Well, the damping is the bulk modulus is a scalar. So if you want to increase the damping progressively, you just add some imaginary part to the damping, but increase it progressively when you go away from the finite element region. The radial impedance do not change, so you have to counteract this using a density that remove this effect, so that rho c, the impedance, is not changed. But at the same time, you have to keep the tangential speed of sound the same. So there you have to change the density in another way, so that it's bulk divided by density that do not change. And so that's why you have this density that becomes anisotropic, with a value in the radial direction and another value in the tangential directions. And obviously, to define this radial direction, you can do it by hand, but it's not very automatic for commercial software. So the idea would be to just define a distance function and compute its gradient in some buffer zone and do everything automatically. Well, now that you have that, it works well, but you have still to adapt the thickness to the wavelength. Good rule of thumb is that you need to have at least one wavelength of PML to damp efficiently the waves. The same mesh criterion as for finite elements. You also have to refine your mesh with a wavelength for the PML region. And basically, well, you can use adaptive meshing to adapt the PML to the frequency range of interest. Another method is interesting also, it's the infinite elements. There the idea is a little bit different. The idea is to bypass the limitation of the finite elements in terms of paving infinite region by using a different kind of mapping that is traditionally used for finite elements. This mapping will push some edges or face of the elements towards infinity, so that basically you will define an infinite elements that cover portion of the exterior space but extends towards infinity. When you do that, you are forced to adapt also the shape functions because else you will end up with some issues, and you will use oscillatory shape functions because you will have to represent the oscillations of the fields towards infinity. You will also change the test functions to allow easy integration for these oscillations. And there are various tricks there, but I will not go into details. But in the end, you end up with something that is quite similar to finite elements, except that it's applied on a region of space that is unbounded. The big advantage there is that contrary to other absorption methods, you don't only absorb the waves, but also get the pressure field in those strange but similar to finite elements things. So it means that you don't have to do the integral formulation to retrieve the pressure in the far field. You directly have it. And if you are interested in a lot of pressure points in the far field, it can be an advantage because the integral formulation can become costly. Okay, this is an example. I will not go into details, but just to show the type of simulation that was done. Infinite elements are costly. I will show a comparison between infinite elements and PML because that's the main boundary condition we use for dealing with infinite medium, so sound radiation. And the difference and common points are there. For PML, you need to have a volumic mesh in addition to your finite element parts close to the radiating body. But it's not a big issue with modern meshes. You have obviously more degrees of freedom in the PML because you have a real mesh, while for infinite elements you have only the surface mesh, but with a lot of degrees of freedom describing the radial variation of the pressure field. Still, infinite elements use less degrees of freedom, but the bandwidth is larger for infinite elements. And when you combine the two, basically, we found out that PML is more interesting at high frequency, infinite element is more interesting at lower frequency, and naturally when you have something like that, you tend to try to implement some automatic conversion between one condition to the other, depending on the frequency, and that's what we have done. You have also some consideration about the frequency dependency. That is not really important at this stage. Only it's important to know that infinite elements have a version in the time domain. For PML, it's more difficult. It's possible, but you lose a little bit of the efficiency, so you need to have larger PML. Okay, a very quick application for this. Different types of non-reflecting boundary condition when you are interested in sound radiation. The application is extremely simple. It's a rectangular plate, simply supported, baffled with diffuse fields excitation, and you are interested in the transmission loss. I will define it later, but you had a definition yesterday already. So basically we tested finite element plus infinite element plus PML, and also directly the relay surface integral that can be done here because we have a flat plate. And as I said, well, not surprisingly, at low frequency, infinite elements are better than PML. at high frequency, PML are better than infinite elements. It's the case both for memory and for the time. Something to see also is that the Rayleigh integral, even if it increases the solution time because it couples the depth of the plate between each other instead of just having a localized coupling, it's still much more interesting than the other approach in terms of both memory and CPU time, but it's limited to flat structure. Okay, so now maybe more details about the core of the presentation, finite element for porous materials. I spend a lot of time on acoustic materials, not so much for structural elements, but it's normal because for all kind of numerical models, we almost never use porous materials alone. They are always embedded in contact with some vibrating structure and radiating or coupled to an acoustic cavity. So it's very important to be able to couple those porous material to numerical model for structures and for acoustic radiation or fluid cavities. Okay, you've seen how I've derived the finite elements for fluids. Basically, the idea for porous material is exactly the same. We start from a PDE. We create a weak form for this PDE, do some clever use of the green theorem and do partial integration and end up with a weak form with natural boundary conditions. And then we discretize this weak form. The trick is to use a PDE and apply the green theorem cleverly so that the boundary condition, the natural boundary condition we get are useful, either as themselves or because they allow easy coupling. And Noureddin has spoken about that yesterday. I will just repeat things a little bit now here. But I will not go into details about the various formulation. Why? Because we use exclusively the UP formulation, and more exactly the second variance of the UP formulation, the one that couples naturally to other porous materials and to solids. Why? Because it's much more easy to couple with all our materials. Coupling with solids, with the fluids, is not really difficult. It's just adding a contribution that we have to add already when we couple solids to fluids. So it's UP materials will be considered exactly like solid materials within the code, except that they carry pressure degrees of freedom in addition to the displacement. They are much more efficient in terms of degrees of freedom than the other formulation based on fluid displacement, because they go from 6 to 4 degrees of freedom per node. And the natural boundary conditions are also useful in the sense that they naturally express total stress and allows easily to impose impervious membranes on the surface of pores. That's why they couple easily with solids, and that's why they are useful in themselves also as natural boundary condition. Something I will do also here, but very quickly, I will not go into details, is use anisotropic biomaterials. Why? Because basically, of porous materials, they are often anisotropic. We assume them isotropic because anisotropic properties are difficult to measure, and anisotropies can often be neglected. But still, it can be important for some cases, like array of ducts that I will hopefully speak about later, or very thin membranes that have anisotropic behavior for the elastic behavior, where you have shearing and bending or compressive behavior that can be different. So it can be important, and basically, as you will see, it comes at no additional cost. So why go to isotropic bio when you can do anisotropic? Okay. I will not go into details about the basic assumptions of BO because they are exactly the same as what you have seen a few times yesterday already, except that we assume full anisotropy of the skeleton behavior and the resistance, both, well, the coupling terms, both viscous and inertial. So the resistance and tortuosity can also be anisotropic. Typical use case I already told you about. It's to have the possibility to implement anisotropic behavior for the skeleton of thin layers, some honeycombs or other array of ducts where you have anisotropy for the resistivity, but a special kind of anisotropy. Basically, you have some direction in which the resistivity is infinite or the conductivity is zero, if you prefer. You are completely blocking the fluid in some direction, and this happens quite often. Derivation, it's exactly like the classic isotropic BO derivation for the UP variants, the second variant of UP formulation, except that at some places you introduce tensors instead of scalar to take into account the anisotropy. So, for example, one of the main sources of anisotropy is the interaction force between the skeleton and the fluid. Usually, it's just a drag force that is the same in every direction. Here, we introduce a tensor so that the force can be non-aligned with the relative velocity between the two phases. You do the same as for isotropic BO, but inverting second-order tensor when needed. And you end up with something that is very, very similar to the formulation you have seen yesterday, except that you have elastic behavior that can be anisotropic, so it's a fourth-order tensor, completely general. And you have densities and coupling terms that are anisotropic, that can be anisotropic also. Well, can be because when you can use anisotropy, you are not forced to use it. You can just define tensors that are isotropic and you fall back to the isotropic BO formulation. Okay. Some tricks we use also, but you have various ways to do that. We like to have a symmetric formulation because it's more efficient for implementation, and it uses, well, we can halve the CPU time doing that. So we don't use directly the pressure, but we use a scaled pressure, which is basically velocity potential. And this makes the coupling term symmetric, and it takes the form of a damping coupling term, or it has a E omega dependency, which is also nice because we now have something that is under KC omega formalism, and we end up with such matrix everywhere for coupling fluids, solids, and so on. So that's how it looks in the end at the element matrix level. Again, I will not go into details, but just know that this is something that is quite similar to what we have for solids for this part, or for fluids for this part. Numerical validation, again, I will not go into details, but how we have validated this anisotropic, cross-validated this anisotropic model, not by comparing with the experiments, but just comparing with the isotropic model, but using 1D excitation. So we can just rotate the anisotropic properties and check that it gives the same as isotropic model when the other directions are not excited. And it works. Also, when we use infinite resistivity, we wanted to check that we fall back to a solid behavior where the bulk modulus of the solid is the bulk of the skeleton plus the bulk modulus of the air, but you don't have any relative motion between air and skeleton, so you don't have dissipation into the air. Okay, another more complex example, just to show that anisotropy can have an effect. I have used an isotropic porous and a transverse porous that have the same properties in the normal direction, but infinite resistivity in the tangential direction. And as you see, response can be quite different, and the shapes of the deformation of the porous media can be quite different also at the same frequency. Just for an illustration. Okay. As a conclusion, I would say that modeling an anisotropy with finite element is completely painless, but measuring and defining anisotropy is not painless. Isotropic porous material already contains a lot of parameters, as you have seen yesterday, that are difficult to measure and that contain some variability or uncertainties. If you multiply this using full anisotropy, it becomes extremely complex, and very few people will measure anisotropic properties fully. So why we developed those anisotropic porous? Mainly because we want to use them for restricting relative displacement in one or two directions, and being able to use anisotropic or transversely isotropic mechanical properties for the skeleton. That's the main reason we have developed that. And you will see, maybe if I have time, one use of those anisotropic equivalent fluid, so forcing the displacement of the skeleton to zero, but using this anisotropic equivalent fluid later on. One use already you have seen for this equivalent fluid, the anisotropy in the equivalent fluid is the PML itself, where we have used anisotropic density, so it's related to this development too. Okay, so as a nice illustration after all those equations, and I will end by that, but I will not go into details here. I will show how we can use finite element modeling to have access to internal information about the behavior of the material. This is something that is very difficult to do experimentally, but that can be useful to understand what happened, especially as porous material are used for their damping performance. So having access to some damping or energy flows information within the material is interesting to understand what happened. Okay, it used the model I've just spoken about before. And as I said, using Galerkin finite element formulation is nice because it has some kind of equivalence from the energetic point of view. How does it work? You can get the dissipated powers or stored energy directly from the Galerkin formulation. Here is an example. It's very mathematic. I will not go into details, but you can, for example, express the viscous damping as an average of the viscous or interaction force times the speed difference. This is the work of the interaction force between the skeleton and the fluid. Do a lot of manipulation, and you end up seeing that basically this viscous damping is the imaginary part of the sum of the matrices I've shown before of the Galerkin formulation with the solution you have get from your finite element model times the solution conjugated. And you have this term here for the fluid, so the pressure here, or scale pressure, for the skeleton displacement, and for the interaction term. Here it's the real part instead of the imaginary part. This is quite useful because those matrices have been computed already for solving the problem. So basically the energies come not for free, but they are not costly to compute. And the other interesting thing is that if you do energy balance at the discrete level, well, obviously energy balance will be fulfilled at the continuous level, else you will break energy conservation. But at the discrete level, it's not so easy. It depends a little bit how you evaluate your energy. And if you use directly the same matrices as for solving the problem, you can guarantee that your energy balance will close exactly, and that's interesting. So just a very simple illustration here. It's an elasticity test of a simply supported plate that is excited by its perimeter, covered by porous material and a heavy layer. Quite classical configuration, very simple geometry. The properties here. This is the dissipated power in the whole system, and as you see, for the properties I have chosen, you still have a quite modal behavior up until this frequency where you start to have some kind of damping that is so high that you lose all the modal behavior. And you can check what happened here more in more details at those eigenfrequency to see a little bit how the dissipations works for this system. So the first sandwich mode, well, basically the porous material do not really behave like a porous material. It acts like a sandwich core, a structural sandwich core. The presence of fluid has no impact on the stuff, and most of the damping, as you've seen here, comes from the internal damping within the skeleton, structural damping. So basically, you could do that in vacuum, and you would end up with something very similar. Then the first longitudinal sandwich mode still behaves as a sandwich. You have a little bit more viscous damping, but not so much. Also, yes, something interesting to see is that the two dominating damping mechanisms in this case, they are the viscous damping, that especially at higher frequency, that becomes dominant here, and the structural damping. All the other damping mechanisms, thermal losses, damping in the aluminum or septum, can mostly be neglected. The septum is a little bit important here, but still those are the main, the two, viscous damping and structural damping, are the main damping in this case. Okay, so here still structural damping. When damping increases, the mode becomes less distinct. It's not easy to see because it's very small, but as arrows you see the flow displacement within the porous material. The color map is for the viscous damping, and obviously the deformation is shown. Okay. When you reach 232 Hertz, something very interesting happens. You start, and this is where modal behavior stops. You start to have decoupling between the top and bottom layer. Basically, it's the pumping frequency, and you see that there you start to have viscous effects that dominates, at least in some region in the edge. Why? Because you have differential deformation due to the edge effect between the sides of the heavy layer and the center, and so fluids have to move to fill the open or closed volumes, and this induces a lot of viscous dissipation. So it's what I call a ring effect here, and you will see that it will persist longer. When at 400 Hertz, the heavy layer completely decoupled from the plate, and the viscous effects completely dominate from the ring here. You have less, well, you still have dissipation from the structural behavior, but most of the dissipation occur because of this fluid displacement. And this is really linked to the edge effect. So you could not have that for an infinite plate. It will be dependent on the boundary condition you have here. So here I have natural boundary condition. It means an impervious condition. You have no fluid entering here. But if I couple this with fluids, the damping will increase because more fluids will move, basically. So edge effects are really, really important there. Well, I have nice animation if I... Okay. So This is the real resonance, the 1D pumping, and there also the main damping comes from the ring effect. Fluids move from the outside, from the inside, due to the difference in deformation on the sides and on the center. Above that, you start to have so much decoupling that your top and bottom plates start to behave independently, and you have wavelength different on the top and the bottom. And you have a lot of damping due to that, because it means the separation do not happen exactly at the same position, and you have some gaps that are created, some extension that is created, some compression, and fluids move a lot in the different direction. Viscous effects dominates. Heavy layer is very well isolated, and the trim is extremely efficient. Okay, some animation again. So you see that it's not modal, because damping is so high. It's more like you create waves at the boundary, and those waves propagate towards the center. That's really what's happening. Okay, so in this case, infinite plate model will start to become a nice model again, because you still have a side effect, but even within the center of the plate, the decoupling is large, and you will model well the damping linked to the fluid motion. Okay, so conclusion: an isotropic bio is not more costly for an implementation point of view than isotropic. So we have it. We not use it directly because usually the properties are not known. So it's more used internally to represent other things. Galerk infinite elements allow very easily to post-process the result in terms of energy, and that can help a lot for understanding physical phenomena. So I think I will stop now, and we will continue later in 30 minutes for some numerical applications.